Hello, space enthusiasts and curious minds. Today, we're diving into one of the most intriguing questions in physics and science fiction. Can we detect faster than light travel? Let's explore what current science says about surpassing the cosmic speed limit and whether it's scientifically plausible or just a fantastic dream. Dr. Dietrich is renowned for his research on the physics of compact binaries and multi-messenger astronomy, exploring the fascinating interplay between numerical relativity, gravitational waves, and Killian-Noah modeling. Dr. CL's work focuses on solving Einstein's theory of general relativity through numerical methods, within both cosmological and astrophysical contexts. Stay tuned as we explore some of the most captivating developments stemming from Einstein's theory of relativity. And don't forget to subscribe to Event Horizon to ensure you never miss an episode. Welcome, Dr. Katie CL and Dr. Tim Dietrich. Thank you both for joining us today. The concept of the Alcubierre warp drive metric revolutionizes our understanding of potential space travel, hinting at the tantalizing possibility of traversing the universe at speeds surpassing that of light. This theory posits that we might, theoretically, bend a segment of space-time itself, allowing it to move faster than light, while a spacecraft nestled within this warp bubble carries passengers across cosmic distances. Here arises a pivotal question regarding the Alcubierre drive. Is there a speed limit, or could we potentially achieve unlimited velocity? Theoretically, the speed is limitless. However, surpassing the speed of light might introduce complex phenomena, such as the creation of closed time-like curves, which could allow for backward time travel, a concept that current theories suggest might be improbable. Although this framework suggests you could travel at unimaginably high speeds, practical experiments and simulations have yet to reach even the speed of light. This boundary between theory and application invites us to explore and challenge the very fabric of our understanding of physics and the universe. In our latest research on warp drive technology, we've actually concentrated on speeds below that of light, rather than attempting to surpass it. This leads us to an intriguing possibility. If there weren't a natural barrier at the speed of light, commonly referred to as could we face regulations to prevent potential time travel paradoxes and the creation of closed time-like curves? Indeed, there have been suggestions that once we approach the speed of light, new physics might emerge, potentially destabilizing space-time itself. From the perspective of classical physics and general relativity, there's no clear mechanism that would prevent exceeding the speed of light. However, introducing quantum physics into the mix, particularly the relatively unexplored territory of quantum gravity, could offer reasons why traveling faster than light might not be feasible. The intersection of quantum effects with classical theories might reveal constraints that are not immediately apparent from Einstein's equations alone, suggesting that the universe may have its own set of rules to prevent the theoretical extremes of warp travel. Traveling at high relativistic speeds, like 90% of the speed of light, could potentially be more achievable and energy efficient with warp drive technology compared to traditional propulsion methods. This suggests a significant energy saving by not having to accelerate an object to such speeds through conventional means. However, the feasibility of this depends largely on the specific warp drive metric utilized. For instance, the model we've been working with might require an amount of energy equivalent to the mass energy of our Sun just to power a kilometer-sized warp drive. That's an enormous energy demand. There are designs for warp drives that require less energy, but these still represent a substantial investment. Moreover, while warp drives eliminate the need for conventional rocket fuel and propulsion, they introduce their own set of challenges, such as the necessity for negative energy. This poses significant physical and technological hurdles. Therefore, for civilizations more advanced than ours, directly accelerating to high speeds might prove more efficient than developing warp drive technology. In essence, while warp drives offer an intriguing alternative to traditional space travel, they come with formidable energy and technological requirements. The creation of a warp bubble introduces an extraordinary and complex geometry to space-time, allowing us to theoretically manipulate it in ways previously confined to science fiction. But the real intrigue lies in detecting these phenomena, particularly through gravitational waves, which might not occur as we first thought. Indeed, our research suggests that a warp drive traveling at a steady speed and direction doesn't emit gravitational waves due to the lack of a quadrupole moment, which is necessary for such waves to arise. Gravitational waves typically require oscillations, such as those generated when a warp drive is either accelerating or collapsing in a rather chaotic manner. When it comes to actually observing these effects, while the warp drive is in motion, no gravitational waves are produced. However, any irregularities, like the sudden collapse of the warp bubble, could be detectable. This raises the question of whether our current gravitational wave detectors, like LIGO, are equipped to pick up such subtle and transient signals. For deeper insights into this, I'd defer to Tim, our expert on LIGO, to explore whether we currently have the sensitivity required or if further advancements are needed. Certainly a key factor in detecting warp bubbles through gravitational waves hinges on the frequency of the emitted waves. A warp bubble about 1 kilometer in size, for example, would emit gravitational waves at a relatively high frequency, somewhere in the range of a few hundred kilohertz. In contrast, our current detectors like LIGO and Virgo are tuned to detect frequencies around a few hundred hertz. This means that the gravitational waves produced by kilometer-sized warp drives, or even smaller ones, are simply too high frequency for our current technology to catch. Interestingly, as the size of the warp bubble increases, the frequency of the emitted gravitational waves decreases. This suggests that a planetary-sized object might fall within the detectable range of current instruments, yet no such signals have been observed to date. To truly capture the higher frequencies associated with typical science fiction-sized spacecraft, we would need a new generation of detectors specifically designed for these higher frequencies. As for the future of gravitational wave detection, the main trajectory of advancement is towards lower frequencies, not higher. The planned space-based laser interferometer aims to push sensitivity to even lower frequencies. This shift highlights a gap in our current capabilities and the need for innovative solutions if we are to detect the more elusive, high-frequency gravitational waves indicative of warp travel as depicted in our favorite sci-fi tales. The pursuit of detecting gravitational waves at the high frequencies generated by hypothetical warp bubbles is intriguing, yet it poses significant technological and financial challenges. Currently, the next generation of gravitational wave detectors is slated to operate at similar frequency bands as the existing LIGO and Virgo instruments, which won't help in capturing these higher frequencies. There have been proposals to develop detectors that could potentially capture the range needed for our theoretical warp drives. However, these are still in the early stages of development, and no clear funding path exists to bring these ambitious projects to fruition within the next few decades. Katie has delved into the research and proposals in more detail, indicating that while the technology may exist, the funding does not, largely because the expected astrophysical signals at these frequencies are scarce. The real excitement lies in the possibility that detecting anything at these high frequencies could indicate something truly extraordinary, such as primordial black holes, cosmic strings, or other signatures from the early universe. These phenomena straddle the realms of fundamental physics and the fringes of our current understanding, including theories beyond general relativity and the Standard Model. Thus, while the financial support for such detectors may lag, their potential to uncover new physics could add a compelling layer to their justification. If something is detected at these higher frequencies, it could very well rewrite our understanding of the universe. The possibility of discovering new physics through high-frequency gravitational wave detectors is both tantalizing and speculative. While the potential for groundbreaking discoveries exists, the speculative nature of the sources has hindered funding for these projects. Tim tends to be more skeptical about the chances of detecting anything. Though I share some of his skepticism, I also believe it's an area worth exploring. The excitement lies in the unknown. If we did detect something at these high frequencies, it would signify a monumental breakthrough, indicating phenomena we currently can't explain. This could range from primordial black holes to cosmic strings or other early universe signatures, essentially new physics beyond our current models. Serendipity has always played a crucial role in scientific discoveries. Often we stumble upon the most profound insights while searching for something else entirely. In this spirit, even if the likelihood of detecting these high-frequency signals seems low, the potential payoff is enormous. Moreover, the beauty of scientific research is its versatility. We can piggyback different studies onto existing projects. For instance, using radio telescopes and radio astronomy alongside gravitational wave detectors allows us to maximize our chances of uncovering new phenomena. By casting a wide net, we increase the odds of stumbling upon something extraordinary, even if it's not what we initially set out to find. Imagine we're studying the hydrogen clouds in the Milky Way with radio telescopes. While our main focus might be on these clouds, the data collected can be re-examined by other scientists who might discover something entirely unexpected. This cross-disciplinary potential is what makes the cutting edge of physics so exhilarating, especially when it comes to gravitational waves. Gravitational waves represent a frontier of modern physics. Not long ago, we hadn't detected any, and now we're observing neutron star mergers and other fascinating phenomena. This new realm is brimming with potential discoveries, making it one of the most exciting fields in physics today. Now consider the implications for warp drives. If a warp drive were to exit warp, we would expect to see a distinctive signature in the gravitational waves. But that might not be the only clue. There could also be a burst of radiation emitted at the same time or shortly after. This dual signature, gravitational waves paired with radiation, could serve as a confirming observation, providing solid evidence of a warp event. This possibility opens up a whole new avenue for detection and validation. So yes, while gravitational waves are crucial, we shouldn't overlook the potential for additional confirming observations from other sources of radiation. This multifaceted approach could be key to discovering and understanding these exotic phenomena. In our paper, we discuss an intriguing aspect of warp drives, the fluid that supports the curvature of spacetime around the warp drive. Our simulations show that this fluid, at least in part, radiates along with the gravitational waves, creating bursts of alternating negative and positive energy. The mysterious nature of this warp fluid means we can't predict how it might interact with normal matter. Consider neutrinos, for instance. They pass through us unnoticed, but with the right detectors we can observe them. Similarly, if the warp fluid interacts with normal matter, it could trigger telescopes or other detection methods, potentially producing an electromagnetic counterpart. However, we're still in the dark about the properties of this warp fluid, making it challenging to anticipate how it would manifest as a detectable signal. An interesting possibility is whether this signal could serve as a form of communication. Imagine if shutting down a warp drive could send out a hello message. This concept opens up a fascinating avenue for further exploration, combining the realms of advanced propulsion and interstellar communication. While the specifics remain speculative, the potential for discovering such signals adds an exciting dimension to our search for new physics and technological breakthroughs. Imagine a scenario where an advanced civilization isn't using warp drives just for travel, but as a means of communication across the observable universe. They could create a distinct and powerful signal by deliberately manipulating space-time, curving it intensely in one spot, and then allowing it to collapse, emitting a noticeable burst. This method wouldn't necessarily be about using the warp drive for travel, but rather generating a loud, clear signal. As our paper discusses, if you were inside a warp bubble during a collapse, it would be catastrophic. So it's more plausible to consider this process as a communication tool rather than a transportation one. However, creating such extreme curvature in space-time requires immense amounts of energy. For instance, gravitational waves themselves demonstrate how stiff space-time is. Generating them involves significant energy. Therefore, while the concept of using warp drive mechanics for communication is fascinating, it also highlights the massive energy requirements involved in bending space-time to such a degree. In summary, while I'm generally more skeptical, the idea of using warp bubbles as a form of interstellar messaging is captivating. It combines the awe-inspiring potential of advanced physics with the profound possibility of communicating across vast cosmic distances. To generate signals that are detectable across vast cosmic distances, incredibly large amounts of energy, mass densities, and high velocities are required. The energy needed to create an observable signal through collapsing warp bubbles would be astronomical. While the idea of using warp drives for communication is fascinating, the energy demands are likely far higher than more conventional methods, such as sending bursts of gamma rays at specific frequencies and intervals. Given these immense energy requirements, it's more plausible that an advanced civilization would use warp drives primarily for travel, moving from point A to point B, rather than for sending signals. The energy needed to manipulate space-time to create detectable signals would be enormous, comparable to the energy involved in gravitational wave generation, which often involves massive cosmic events. Throwing stars around or generating significant gravitational waves is an immense undertaking, requiring vast amounts of mass and energy. This has always been a significant consideration in discussions about gravitational waves and their potential uses. It's worth noting that we do have anomalous gamma-ray bursts that have been detected, and while there are reasonable explanations for these, the idea of using gamma-ray bursts for communication remains an interesting topic for further exploration. In summary, while the concept of using warp bubbles for communication is intriguing, the practicalities of the energy required make it more likely that such technology would be reserved for transportation. Nonetheless, the discussion opens up exciting possibilities and underscores the need for continued exploration in both gravitational wave detection and astrophysical phenomena. While these gamma-ray bursts are often astrophysical in nature, the reason I'm curious about multiple simultaneous signatures is that a gamma-ray burst occurring alongside a gravitational wave could provide a straightforward confirmation. However, we can only speculate about what advanced civilizations might do until we actually observe such an event, which could happen tomorrow or in 500 years. We simply don't know. One major challenge with concepts like the Alcubierre warp drive and wormholes is the need for negative mass. Physics doesn't outright prohibit negative mass, and the universe might allow it. But the question remains, could we ever create it? Does anyone even have a starting point for contemplating how to produce negative mass in a laboratory setting? Interestingly, there is a phenomenon in physics known as the Casimir effect. This effect occurs when two mirrors are placed very close together, confining a field between them. This setup can lead to the creation of negative energy density, a step towards the kind of negative mass we would need. While this is far from creating negative mass on a usable scale, it does provide a fascinating glimpse into the possibilities of manipulating the fundamental properties of space and time. The Casimir effect is a fascinating phenomenon that essentially creates localized negative energy. This effect, which you can look up and find well documented in physics, arises from the confinement of a field between two closely placed mirrors. While this demonstrates that negative energy density can indeed be created, the challenge is that the entire system, including the mirrors, still results in a net positive energy. It's incredibly difficult to produce pure negative energy without any positive energy components. Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q&A sessions with experts. Your membership will grant you the chance to participate in live Q&A sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos, and join us in unraveling the secrets of the universe. Become a Blisovia Science TV member today, and together, we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comments.